A robot may not harm a human being or through inaction allow a human being to come to harm.
This is Asimov, or open source humanoid robot. And what we have here is a pair of legs, or technically speaking, a bipedal robotic system. I'm Alex. I'm the mechanical engineer responsible for designing and manufacturing this piece of legs here. What I'm gonna do here is I'm gonna explain or try to solve the question of how did we build this? The first step to build one of these robots is add constraints. A good way to add a constraint is the measurements or the proportions, because this will overall constrain the rest of the system. What I mean by that is we need to determine what's the length of your links. In this case, what's the length from your hip all the way to your knee. These lengths will change depending on the size that we select. But it's actually quite tricky because even from person to person, this distance changes. So that's why I like to use this diagram, which allows me to actually just multiply the factors from the proportions to the height of the robot. So in this case, I have the proportions and I can just multiply for 1.2 meters, which is going to be the height of Asimov. And automatically I can get a full human sketch with the proportions and the lengths exactly as for a human of 1.2 meters. For the next step, once we already have defined our proportions, we need to start defining the actuators that we're going to use for our system. So we start with the proportions because that gives you a really good constraint in terms of the size of the robot, which will also give you a really good constraint on the weight of the robot. This is a little bit of an iterative process because you need to be able to put the motors in the joints desired and being able to calculate the weight that the overall robot will have. Weight is a very important constraint because that will determine how much torque your motor requires in specific joints. So that's what I mean is also a very iterative process because you're going to select the motor, you're going to put it here in the knee, and then you're going to continue adding the other motors into the system. But hey, you maybe realize that now the overall weight of the robot is actually more than what you expected. And now the knee motor is not capable to handle that load anymore. So you need to go back, put another motor, redo the calculation, and now see if it meets. What I usually recommend is adding some safety factors into it. So you can, mitigate problems in the future regarding, adding weight for the cables or adding weight for other sections of the robot that were not previously considered. Sizing the actuator could be a little bit hard. So that's why I recommend to get the first estimations based on the worst case possible of your system. Let's say we're analyzing the worst case for my elbow, right? Which basically will be if my arm is completely extended and I apply a load into my hand, my elbow will receive a lot of this force here. It's the one that is going to be trying to compensate for my hand going down. So this is what I mean by the worst case scenario for determining the actuator torque. You can do this for different joints. This example was specifically for the elbow, but it can be applied for other type of joints in your system. It's either for arms or for the legs. The idea is try to get the maximum values that your system will be working on. These string scenarios that I mentioned might not happen because it's the combination of other joints that are working together to be able to hold the load as I explained. But it's a really good estimation for preventing your joints to being under-specced. Later on, you need to consider other stuff like the structure itself, which is an added weight of it, and probably, if required, rerun the calculations based on that and size again your actuators if necessary. Once we lay out the actuators in the positions that we wanted and we're happy with it, we can start planning how we're going to connect everything together. And this is where a lot of decisions have taken place in order to start this process, because you need to consider things like the materials to use, the manufacturing methods, you have to consider the wiring. How is going to be everything connected to each other? Not only mechanically speaking, but also electronically speaking. The range of motion, right? What's going to be the movement? Where is it going to stop, right? All those decisions have to come together into that stage, which is basically the mechanical design of it. This prototype is quite interesting because it utilizes a term that I like to use, which is borrow strength. What I mean by that is that traditionally you can make this type of robot or these structures by aluminum, right? Like traditional manufacturing methods, but it will be quite expensive and you will be limited of the type of geometry that you can do. So since we're dealing with anthropomorphic robot, we wanted to look human-like. And that's why we utilize 3D printing for it. Of course, not all the robot can be done with 3D printing because at the end of the day is a plastic. And that's why we have other materials in specific parts of the robot to borrow that strength. That's what I meant with that term. That way we have the benefits of 3D printing, right? We can have complex geometries, we can prototype it fast, we can iterate on the design without really having to spend too much on the manufacturing aspect of it. The 3D printing that we have in this robot, it's a little bit different from the 3D printing that we have at home. This is basically industrial 3D printing, and the technology is called SLS, which stands for selective laser sintering. The benefits of this technology is that you can have parts that don't have any layer lines, which means they don't have weak points in the orientation that they're print. They're basically solid. Another added benefit is that these parts don't require supports, which means you can create really complex geometries without worrying if there's overhangs on it or if the overall internal cavities will be supported somehow. Every part that we design has to go through a finite element analysis. This way, you make sure that your parts and the whole assembly can withstand the loads that your system is going to interact with. In our case of a robot, there's a lot of stumping forces, probably some rapid movements where it hits itself. So you need to make sure that the parts itself withstand those. Another very important part of the validation is how other components interact with what you already model here. That's why we can use traditional 3D printing for it. I mentioned that the 3D printing that we have is quite different, but for our purposes of validating the system, this is actually quite enough for us to test the integration of the rest of the components, especially wiring. Wiring is a bit difficult to model. So having the physical part and attach the motors to it and being able to manipulate it in the physical world, it gives you an idea where the wires are gonna go. And this is very helpful for that. Let's talk about the ankle from Asimov. The ankle has 2 degrees of freedom, which is ankle pitch and ankle roll. The way we're achieving this is quite interesting. I really like this mechanism. The name of it is a bit hard to pronounce. It's revolute spherical universal type of joint. And let me try to explain it a little bit so you can also understand a little bit of the naming behind it. This is a simplified model of the ankle mechanism. It's basically simulating the pitch movement that I mentioned and the roll movement that I mentioned. This is achieved by a universal joint, which is those type of axes that are crossed this way, and that way you can generate both movements at the same time. That's the universal side of the naming in the mechanism. The other two is basically the revolute comes from the type of actuator that we're using. We're using a revolute actuator. As you may know, there are other types of actuators like linear actuators, right? In that case, the name changed a little bit, but it's possible to implement them as well. The spherical came from the type of movement that it generated at the end, right? So if we move these 2 degrees of freedom at the same time, it cannot trace like a sphere. So that's why the name of it. And I think it's a very interesting mechanism. If I'm being honest, it was quite challenging to design. So that's why we have a bunch of props around the office and stuff to try to understand it. One more thing I would like to highlight about Asimov is its articulated toe. Asimov has an articulated toe, meaning that it only moves when it's walking or when other forces apply to it. It's not actuated. It means we cannot move it. It's basically just a way for the foot to get contact in the ground. Not many humanoid robots actually have an articulated toe. And it's kind of interesting because when you understand the behind of it, why it's actually a useful thing to have. I believe every robot should have it. Let me try to explain a little bit what I mean with that. If we grab again our simulated mechanism here, we can consider this as our feet. If you're basically taking a step, at some point, you will only have one edge of your feet touching the ground. And for a robot, this is basically where a lot of the propulsion to move forward happen. So the idea behind having an articulated toe is that you're actually going to take step and it will bend in position, which means now it's not only an edge that you have in contact with the ground, but you have a whole area where now your feet has more area to push forward. I believe that's the primary reason of the articulated toe. And when we are exploring different locomotion systems, it actually makes a lot of sense. I hope this solved a little bit the question of how we built Asimov. Asimov is our open source humanoid robot, and we're gonna start releasing a bunch of stuff soon, starting with the legs, and hopefully in the next video, we can show more on the rest of the system, probably the arms, the torso. There's very interesting stuff that is happening behind the scenes. So please check out the description for the rest of the files and more information about the project.
Okay. Let's read the robot.
A robot must obey orders given it by qualified personnel unless those orders violate rule number 1. In other words, a robot can't be ordered to kill a human being. A robot must protect its own existence. After all, it's an expensive piece of equipment. Unless that violates rules 1 or 2. A robot must cheerfully go into self-destruction if it is in order to follow an order or to save a human life.